Hi everyone, in this video we'll be looking into different types of spectras that are produced as electrons in an atom are excited into their excited state or returned back to their ground state. But before I do so, there's one key concept that we need to examine, and that is the electromagnetic spectrum. Now, you may have heard of the electromagnetic spectrum from when you were learning IGCSE physics, or you may recall it from another physics lecture. But essentially, the electromagnetic spectrum consists of 7 different types of waves that are divided depending on their energy, wavelength, and frequency. And you can see that at one end of the spectrum, we're going to have radio waves, and if we climb up the spectrum, we're going to have microwaves, infrared waves, visible light, ultraviolet, X-rays, and gamma rays. And at one end of the spectrum where we have radio waves, we're going to have generally lower energy values, longer wavelength, and lower frequency. But if we climb up the spectrum and go to gamma rays, in this end of the spectrum, waves are generally going to possess higher energy values, lower wavelength, and higher frequency. Now, how do we relate this sort of inversely proportional relationship seen between wavelength and high frequency? As you can see, when we have longer wavelength, these longer wavelength values are generally paired up with lower frequency values. And when we have shorter wavelength values are generally paired up with higher frequency. Now, why is this? This is because the variables frequency and wavelength are related via this equation where we have constant speed equaling frequency value multiplied by wavelength. Now, constant speed, as we all know, light travels in vacuum at the speed of 3 times 10 to the power of 8 meters per second, and this is a sort of fixed constant value that we're going to have in this equation. Now, this constant value of speed is going to equal frequency times wavelength. Therefore, because frequency and wavelength are inherently situated in this sort of inversely proportional relationship, we are inevitably going to have these combination of variables where we have longer wavelength paired up with lower frequency and shorter wavelength paired up with higher frequency. Now, given that we know the electromagnetic spectrum from this, we will now move on to what this video will actually focus on. Now, this video will focus on 3 different types of spectras. Firstly, it's going to look at absorption spectras. Secondly, emission spectras. And lastly, continuous spectrums. Now, absorption and emission spectras are spectras that are generally produced as electrons in an atom are either excited into their excited state or returned back to their ground state. But in order to understand how these absorptions and emission spectras are produced, we need to understand one other key concept, and that concept is related to how in an atom we have different main energy levels and electrons situated in each of these main energy levels. Now, this is a picture of a hydrogen atom, or an atom in general, and we can see that this atom is going to have different main energy level values. It's going to have different electron shells, and each of these electron shells are going to be called main energy levels, and we can denote which number of energy levels we have depending on what we use for the number n. So n is going to denote the nth energy shell that we're going to have. So for instance, if we're looking at the first main energy level, we're going to call it n equals 1. And we know that we're going to have electrons located in each of these main energy levels. Now, what's going to happen is when we shoot light towards these atoms, the electrons in these atoms are going to absorb specific frequencies of light. And depending on which frequency of light that they absorb, they're going to be excited into another higher main energy level. The electrons are essentially, therefore, going to move up from the ground state that they were in, from the original positions of the main energy levels that they were in, into higher energy levels. And this is going to create what is an excited state where the electrons are no longer where they are, but at higher energy values. And the energy value, or the energy shell, main energy level that these electrons increase or go up to is dependent on which frequency of light that they absorb. And what's going to happen when these electrons absorb these specific frequencies of light is we're going to get this absorption spectrum. As you can see, we have this sort of continuous spectrum wherein we have this sort of rainbow color where we have all of these different frequencies and wavelength of light kind of shown in the spectrum, and we have black lines sporadically placed in the spectrum. Now, this is created because these specific frequencies of light has been absorbed by the electrons in order to excite these electrons from where they originally were, from their ground state main energy level, into higher main energy levels. And this we're going to call the absorption spectrum because it has specific frequencies of light missing and absorbed by the electrons. On the other hand, what's going to happen when these electrons actually return back to their ground state, thus fall from the higher main energy levels that they were in, is we're going to get the emission spectra. As the sort of fall happens from their excited main energy level state to their original lower main energy level state, we're essentially going to get specific frequencies, photons of light being emitted. And this is going to create what's an emission spectrum, where we have specific lines, specific colored lines for specific frequencies. And these frequencies are essentially the frequencies of the light, the photons that have been emitted as these electrons have returned from their higher excited state to their lower ground state. And this is pretty much the emission spectrum and the absorption spectrum summed up.